Hi everybody. It's weird to be speaking to my computer, but I'm pretty sure you're there. Um, I'm Raphaël GALICHER from the Paris Observatory, and I will talk about focal plane wavefront sensing. So the objective is to do high contrast imaging with a difference of luminosity going from 10 to 9 to 10 to 10 at a fraction of arc second. And the objective is to get images of exoplanets. So today we can image young Jupiter-like planet in the external part of their system, and the objective is to go closer to the star and detecting lighter and older planets, meaning fainter planets. So for that, we are using and we plan to use coronagraphs and extreme systems. So we'll go very fast, but today we have very good classical adaptive optics, I mean scale systems. The objective is to correct the field very close to the optical axis. And we get very, very high strain, but it's not perfect, and we still have aberrations. Okay, I don't know if you can see my mouse, I hope so. So you still have aberrations in the science channel, meaning that if you're looking at the PSF, it's okay. But as soon as you put a coronagraph to remove the starlight and probe the vicinity of this object, the starlight is not perfectly rejected and part of it goes through, and so you have speckles in your image, and you are stuck to contrast with respect to the star that are 10 to 3 to 10 to 5. And this contrast is set by the error residuals and by the non-current path aberration between the science channel and the wavefront channel. And to put some ideas, if you're in H bands, in the 2020 instruments, so today, we have about 1 nanometer RMS at each spatial frequency, meaning that we have a contrast of about 10 to minus 5 in the chronographic image. But if you want to detect an Earth-like planet, it means you need a contrast of 10 to 10. And so you need to have aberrations that are smaller at each frequency than 3 picometers. So let's look at these error residuals and NCPAs that are inducing the speakers. And actually, there are also amplitude aberrations that I haven't talked about yet, but now I do it. So we have amplitude aberrations in the pupil, and these ones are unseen by the AO systems. And the residual contrast in the coronagraphic image is roughly equals to the variance of this amplitude. About the non-common path aberrations, it's the same thing. The residual contrast is roughly equal to this variance of the NCPA phase. And for the AO residuals, imagine that this residuals is changing at each coherence time of the turbulence. Then if you record a long exposure, they will average, but they will not completely average because the exposure is never infinity. So let's say we have an exposure time that is n times the coherence time, then the residual contrast will be the variance of the error residuals divided by the square root of n. Meaning that if we have about a system, an AO system that gives a residuals of about 1 nanometer and a coherence time of 3 milliseconds, then we will need to wait for 1 hour to reach the 1 picometer that gives a 10 to 10 contrast. So first conclusion, we need to use long exposure and very efficient AO system before the science instrument, so that this third term will average correctly. And also we need to estimate and compensate any aberrations in the science channel to get rid of the NCPA and the amplitude aberration. So I will just focus on this second part, estimate and compensate aberrations in the science channel. So the problem is we want to reduce all the aberrations in this channel, meaning that we need to estimate it from the coronagraphic image. And we have the intensity here. while we want the electric fields. So we need a focal plane wavefront sensor that will extract the electric field from the intensity, and then we will control the RTC and playing with the classical AO system so that we can compensate all the aberrations inside the science channel and not only inside the AO system. So there are several wavefront sensing, focal plane wavefront sensing. Some of them are spatially modulating the speckle intensity, like the self-current camera that I will call SCC. Some of them are modulating in time this speckle intensity, for example, the pairwise probing technique that I will call PW. And then once we have estimated the electric field in the chronographic image, we need to control the DM so that we minimize the starlight in the science image, and I will use the electric field conjugation technique in the rest of this talk. And the objective of our study was to compare in laboratory, two techniques, one that is using the temporal modulation and one that is using the spatial modulation behind AO residuals. And to do that, we use the THD bench. THD is for terrific high dynamic bench. And the idea of the bench, here you have the design, I will not go through, but the idea of the bench is to compare several techniques, coronagraphs, focal plane wavefront sensing, focal plane wavefront control, low order wavefront sensing, controlling different mirrors. We have a tip tilt, we have several deformable mirrors, and we can put apodizers in the pupil plane. We can use several coronagraphs, and we also have an atmospheric residual wheel that look like this. So this is the full wheel, the phase screen, and if you look at the size of the pupil, which is the white circle, you can see that we have a large phase screen so that we can rotate the phase screen, and so we simulate optically the residuals of an AO system that would be a very good sexosphere-like system in good conditions. So we do that, and if you do rotate the wheel and you record the chronographic image, you will obtain the movie on the left where we've frozen the turbulence. So this is not what we will get on the telescope. I mean, it's what you would get on the telescope if you're doing kind of millisecond exposures. But if you're doing a finite exposure, you will get the middle image where the AO residuals have averaged mostly. So you can see a halo, but you can see that still speckles, and these speckles are the residual speckles I was talking about earlier if the exposure time is not infinite. So this is only if you have AO residuals, but on our tests we wanted to add quasi-static aberrations, phase and amplitudes over an halo over an halo, and we wanted to correct for these statics and to be sure that we can correct for these statics even if there is a halo of adaptive optics. So what we did, we actually started from this situation where we have quasi-statics over an halo residual, and we tried the two focal plane wavefront sensors that I was talking about earlier, the self-current camera and the pairwise probing, coupled with the EFC controller. And then we tried to minimize the speckle intensity inside the chronographic image. So on the left, on this movie, you have the statics plus the AO residuals for several finite exposure. So there is no correction, so for sure you are limited by the speckles. Then in the middle, you have the correction using the temporal modulation of the speckles, and on the right is the spatial modulation of the speckles. So I will just go back and come back, and here you can see the correction going, and you can see that most of the quasi-static speckles are corrected. So we can correct for the quasi-static even if we are recording images behind an AO system with residuals. There is one point here. In this movie, I just showed you, I will do it again, each iteration of the correction. But actually, if I do it in real time, you will get this movie. And you can check that in the middle, it's going a lot slower because the pairwise probing technique is using several images in time to do one iteration, meaning that you need to record at least 4 images to correct at least once the quasi-statics. While for the spatial modulation, you can do one correction for each image that is recorded. So now I will plot the contrast, meaning the standard deviation, the azimuthal standard deviation as a function of the angular separation from the optical axis, so from the star. In black are the curves for the images recorded with the statics that are not corrected. So this is the initial level. Then in blue is the levels that we get if we add no statics. So it's the point we can get at best. And then in green and red, we have the different iteration using the 2 focal plane wavefront sensor, and we can see that both of them get to what we can reach. So meaning we are able to correct for quasi-statics using focal plane wavefront sensor behind AO residuals. And I think I will just stop here. So it's working. We noticed what we could expect, but it's the first time we really compare things under the same circumstances. So temporal modulation works. Actually, it converges a bit further, a bit faster, but it needs more images. So in total, it's going slower than the spatial modulation. And so the next step is now to do that on Sky. So we started already. We did some tests for the spatial modulation at the Palomar telescope. And we did some tests with the temporal modulation at the sphere, on the sphere instrument in the internal source. And what we get is something like this. So at the top is the Palomar before and after the correction of the speckles in the chronographic image. You can see that very good improvements. And then at the bottom are the corrections that we could get using the pairwise and EFC at the sphere telescope, at the sphere instrument, at the VLT. So before on the left and 2 after. One we are correcting all the field of view, and one we are correcting only half of the field of view. And so the next step now is to go on Sky. Thank you.
Excellent. Thank you so much, Raphaël. It looks like we have one question for you right now on the Slack from Olivier. Olivier wants to know, for pairwise probing, do you need the probes to be larger than the AO residuals? And how are the probes compared to the standard THD2 bench operations?
Sorry, a car just passed by and
no problem. Olivier wants to know more about the pairwise probing. So do you need those probes that you're using to be larger than your AO residuals? And then how large are those probes compared to the standard THDT2 bench operations?
Larger in level, they mean? Okay. So yeah, you need to modulate the speakers. So what is important is you can correct only down to the level of the averaging of the AO residuals. So if your AO residuals is too high, it's useless to do focal plane wavefront sensing trying to correct for statics, because you will be limited by the AO residuals that is not averaging. So it's I cannot give a number because it depends on what level you want to correct.
Sure. And so I had a question for you. You said that, I believe you said that the bench also hosts several different chronograph architectures. Is that correct?
Yeah.
And so the work that you're showing here and the work that you've done this with, is that with different types of chronographs, or is this with simply implementing EFC to dig a dark hole? What sort of architectures have you been implementing for this work?
So the images I showed here are obtained with a 4-quadrant phase mask, but we tested the self-current camera and the pairwise probing with different kind of chronographs. The self-current camera has been tested with a lot of chronographs, actually, 4-quadrant phase mask, 6 levels phase mask, or 8 octants, vortex, and I'm wrap vortex and others. And the EFC also has been tested with vortex and phase masks. So we can use the techniques with different masks. There is no problem.
Right. Okay, well, thank you very much. I think then, if we have no other questions, we'll go ahead and thank you again. That was a great talk.